In the previous video, we calculated variance and used it as a way to talk about the spread of a variable. And at the end of that video, we finished with calculating the standard deviation just briefly. So here I want to talk more about standard deviation and walk through a calculation of that, and then talk about why we might use standard deviation compared to variance. And so as we saw at the end of the last video, the standard deviation is simply the square root of the variance. So the square root of variance is the standard deviation. Okay, so obviously these two are highly connected. So as you calculate standard deviation, you in the process calculate variance. So it's just one more step at the end, again, as we saw in the last video. Now, as we'll turn to at the end of this video, there are reasons why we might describe a variable in the standard deviation compared to talking about the variance. But they serve much the same purpose. So to illuminate this, let's walk through another example, and let's go through the process of calculating standard deviation. Let me just, again, for repetition's sake, let's write down again the formula for variance. So variance is, we're going to sum up the deviations, the squared deviations. Right, we're going to sum up the squared deviations, and we're going to divide by n. And now this is, we haven't talked about the difference here, but this is the population variance. And we'll see in future videos that there's a slightly different calculation when we're talking about a sample. But the process and the concept remains the same. So all it is for standard deviation, and just to, we call this sigma squared, and the standard deviation is simply the square root of all of this. Still taking the deviations from the mean, and that we just refer to as sigma, right? So the square root of sigma squared is just sigma. Okay, so let's jump into an example. Now let's just to work through this, let's think about a variable, and we have income. Okay, and we have income in thousands of dollars. So we'll just label it as K. Sometimes you'll see that as the shorthand for thousands. And we have, let's say some people make 20, 30, 36, and 22. We'll see how difficult I made this on myself. Okay, so how do we find standard deviation? Well, again, we go through the process of finding variance. So just like we did in the previous one, we want to do x minus mu, right? Where mu is the mean, and again, this is called a deviation, right? So this is why we call it a standard deviation. How far does each of these observations deviate from the mean? Well, first we need to find the mean. So 20 plus 30 plus 36 plus 22 is, let's see, 108. Is that true? That's what I'm going to go with. You can correct me if I'm wrong, but that's going to make our mean. It's going to be 27, right? So 108 divided by 4. 108 divided by 4, our number of observations. It's supposed to say 108. And that's supposed to be a 4. Okay, so we have a mean of 27, and so now we simply walk through, and we, as you get more familiar with this, you can kind of smush these two processes together, or two columns together. But here we have 20 minus 27. So that's -7, and that's going to be 49, right? And this is going to be +3, So 9, positive 9, which is 81, and negative 5, which is 25. Okay, and now we need to sum those up because we're going to take an average, right? So we are at the process, we've now found this for each of them, but we need to do the sum and divide by n, right? This whole summing and dividing by n is simply what we've been doing with taking the mean, right? So we are taking the mean of all of the squared deviations. Let's see, I'm gonna cheat a little bit and use a computer to just verify. So this is 164. Okay, and so the sum is 164, so the variance is simply 164 divided by 4, or 41. Okay, so we now have a way to describe this variable of income across our 4 observations. We would say, or our 4 people here, and we would say they make an average of $27,000 with a variance of 41,000. But as we said, we can take this and simply do the square root of the variance. That's going to be the standard deviation. Okay, and the square root of 41 is 6.4 roughly. Okay, and so now how we would refer to this is a mean of 27,000 and a standard deviation of 6,400 or 6.4 thousand. So both of those are legitimate ways to talk about this data, and they describe the data in front of us. There are times in statistics where we will use the variance, and there are times when we will use the standard deviation. And specifically, some of those come up when we're using those in kind of deeper calculations or deeper analysis. Sometimes we require the squared version, right? The sum of the average of the squared deviations, and sometimes we require the standard deviation form. And so neither one is completely set aside. Now I do want to mention one important reason why you'll often hear people describe variables, and remember that's kind of what we're focusing here on in chapter 3, is how do we describe variables? Well, often people describe it in terms of standard deviation, and a big reason for that is the following. Right now we're talking about our values in thousands of dollars. Our units are thousands of dollars, and if we go through the process of recalculating this without that, or I should say in the dollars unit, let's see if we'll see how we do here with the gross math. But our income, just gonna change colors here so we pick up the difference easier. Okay, so our income in just dollars, well, maybe have to jump back here. 20,000, we had 30. We have 30 and 36 and 22. Okay. So when we change the units, the process remains the same, right? And so that the average is not going to change, right? That's still 27,000, but it's going to be written out fully this time, right? And so when we think about x minus mu, it's now going to be, so this is going to be negative 7,000. And this is going to be 3,000. What is this? That was a 36. So that's 9,000 and negative 5,000. Okay, and again, remembering one of the reasons we have gone to the squared version of the deviation is, and you can always check and make sure you've done the deviations correctly, because these should sum to 0, right? And we have that checks out. Okay, so here's where number one, the math gets a little gross. So what is the squared? I'm doing this just so I by a computer just so I don't forget some zeros, but the squared deviation here is 49 million. Right, there's 6 zeros after this. Okay, and the rest remain is also right. So 9 million, 81 million, and 25 million. Okay, when we sum that up, again, it's going to be what was it before? 164 million. Okay, so nothing really drastically is changing here, right? Now, obviously, this is easy when we're scaling up by factors of 10. But we have 164 million. The average of that is going to be, it's also going to be 41 million. So our variance, let me just write that down here. The variance is 41 million. Okay, so now if we wanted to describe this situation, we would say, or this variable, we'd say there's an average or mean income of 27,000 and a variance of 41 million. That gives us the information, but 41 million doesn't give us a lot of insight as to how spread out that is. Now, we can obviously still compare this to another set of incomes, right? Say we have another group of people and they have an average of 32,000 and the variance of 16 million. We would know how to order these two variances, but the variance itself being at 41 million is kind of, it's scaled up quickly. Now, when we take the square root of this, if we take the square root of 41 million, I'm just going to shorthand it as m. When we take the square root of 41 million, we get, again, 64, oops, I gotta zoom down there, 6403, okay, or 6.4 thousand or 6,400. Notice that's the exact same as we had in the previous one, right? Just scaled up. So we had 6.4, 6.4 thousand. Here we have 6.4 thousand, 6,400. The variance has ballooned. It's still, so in the previous one, we had a variance of 41. Here we have 41 million. So the reason for this is, let's think about what units we are talking about. So in the initial analysis, we are talking in thousands of dollars, right? All of this, let me just change colors here. All of this is in thousands of dollars. What that means is that the deviation is in thousands, but the squared deviations is in thousands of dollars squared. Okay, and notice the variance never leaves that thousands of dollars squared. We just take an average of thousands of dollars squared. So the variance here is 41 thousands of dollars squared. The standard deviation comes back to thousands, right? When we take this square root, the units are square rooted as well. So it returns back to 6.4 thousands of dollars. And so standard deviation is in the same units as our variable. So that's a big benefit of standard deviation over variance when we want to describe a variable. So again, highlighting what happens when we change the units. Now we are just in dollars. That's all well and good, but notice, so dollars, this is all in dollars, this is in dollars. When we come up here, we square this, and now we're in dollars squared. Again, that means the variance is in dollars squared, but the, I didn't really label this, but the standard deviation, the standard deviation has returned to dollars. So again, it's in the same unit. Another way to think about this is that standard deviation expands or increases when we have a unit change. It matches the unit change, right? So if we had instead increased by 10, a factor of 10, it would increase by a factor of 10. The variance goes by the squared. So in fact, so what did we do? We went from dollars. Well, we went from thousands of dollars to dollars. That's not the thing I wanted to write. We went from thousands of dollars to dollars, and our so that's a factor of 1,000, right? And what happened? Our standard deviation changed by a factor of 1,000, right? It went from 6.4 to 6,400. But our variance increased by 1,000 squared, right? That unit change got squared, and what's 1,000 squared? Well, it's 1,000,000. So we went from 41 to 41 million. Okay, so that's really the big difference between standard deviation and variance as far as describing variables goes. In addition, and we'll turn to this in a future video, is standard deviation brings with it what's called the empirical rule, and that's pretty powerful if we have what's called a normal distribution. And as we'll see in future chapters, we're going to run into the normal distribution quite often, and so the standard deviation gives us quick insight into where our data falls.